Hello, welcome to the playlist of lectures on essential statistics for data science. I am Hemakumar Kasala, and in this lecture I explain you all about point estimate and confidence intervals. In this video we go about estimating a population characteristic of interest. For example, what is the mean annual cosmic radiation exposure for flight personnel of a particular airlines? Which statistic do we choose and how do we go about estimating the population characteristic such that it is as close as possible to the true value? What is a confidence interval and how does it help augment the point estimate in locating the true value more precisely? It is essential that you have gone through the previous lectures on sample proportion distribution and sample mean distribution in order to understand this lecture easily. This topic is divided into two parts. In this part 1, I explain you the concepts behind the point estimate and the confidence interval. And in part 2, we apply this concept to the above mentioned two distributions and I'll explain how we arrive at the actual values for the estimates. Let's get into the video. What's the mean lifetime of light bulbs belonging to a chosen brand? What population proportion of students favor a fee for recreation facilities in a chosen college? Simplest way to estimate the above characteristics from the respective populations is by using sample data. The estimate of the characteristic of interest is a value which is a single number arrived out of the sample data. The value, that single number, arrived out of the sample data is the value of a chosen statistic for that population characteristic. Statistic can be mean, trimmed mean, variance, standard deviation, etc. For example, 1000 hours is found to be the mean lifetime value arrived out of the sample drawn out of the population of light bulbs of a particular brand, where 1000 hours is the value, in other words the estimate, mean is the statistic, and lifetime is the population characteristic. 1000 hours is the estimate which represent a plausible value of the true population mean for lifetime. Similarly, 0.4 is the sample proportion of students who favor a fee for the recreation facilities. 0.4 is the estimate which represent a plausible value of the population proportion of students favoring fees. These estimates are called as the point estimates. A point estimate of a population characteristic is a single value derived out of a sample drawn out of that population which represent a plausible value for the statistic chosen for that population characteristic. Draw a sample out of the population, choose an appropriate statistic for the characteristic of the population that one wants to estimate, and arrive at the value for the chosen statistic from the sample. Point estimate for the population characteristic of interest equals the above arrived single value for the chosen statistic. It's possible that there are more than one statistic that are available to estimate a chosen population characteristic. For example, to estimate the mean for a chosen population characteristic, one can choose any one sample statistic between mean, trimmed mean, and even median. Let's examine this with an example. Let's take the case of a study involving examining the time spent per week on internet by each student in a college. A sample data for 20 randomly selected students indicate the time spent as shown below. If the aim of the study is to estimate the true mean internet time per week for the college, the sample mean x bar will stand out to be the obvious choice for the statistic. That's not the case though. One needs to consider other contending statistics as well. For example, like trimmed mean, median, etc. Let's evaluate each one of these statistics on the sample data and check how close they are with one another. Sample mean equals sigma x divided by n, and that equals 141.50 divided by 20, which equals 7.075. 10% sample trim mean equals mean taken after dropping two data values each on either ends of the sorted sample data, which equals 112.50 divided by 16, which in turn equals 7.031, and sample median equals 7.0 plus 7.25 divided by 2, which is 7.13. These values are so close to one another, the choice for the statistic should be made carefully. And we will discuss the criteria to choose among the contending statistics in a short while. In certain other cases, not more than one statistic can be used to estimate a chosen population characteristic. For example, to estimate population proportion of a chosen characteristic, the only sample statistic that can be used is the sample proportion. There is no effective alternative in this case. Example is the exercise to estimate the population proportion of students who favor a fee for the recreation facilities. Sample proportion value of 0.4 is the point estimate for the population proportion of students favoring fees. There are no alternative statistics available that can be used in place of sample proportion to estimate the population proportion. The point estimate should be as close as possible to the true value of the population characteristic. The point estimate being a single value of the sample statistic, its correctness in representing the true value of the population characteristic depends on the distribution of the sample statistic. A sample statistic whose distribution is distantly centered from the true value of the population characteristic will more often result in an incorrect point estimate. The mean value of the sample statistic, as sampling is repeated over a large number of times and sampling statistics are averaged, systematically differs from the true value in this case. Such a statistic is said to be biased. An example for a biased statistic is a one that estimates the data range in a population using a sample. Majority of the times, a drawn sample of a fixed size will not include the lowest data value from the population or the highest value or both highest and lowest values. Thus, the statistic that intends to estimate the range using a sample will most often be far less than the population range and hence stays incorrect and biased. On the other hand, sample statistic distribution that is centered at the true value of the population characteristic does not introduce a systematic bias, as the sample statistic in a given instance can be less than the true value and on another instance can be more than the true value. But importantly, the average of the sample statistic, that is, mean of the sample statistics, in other words, mean of the sample statistic distribution equals the true value. However, the variability in the sample statistic distribution plays a major role in estimating the true value of the population characteristic. A point estimate can be far below or far above the true value if the variance of the sample statistic distribution is high. Hence, it's necessary to choose a statistic which does not have a systematic bias and also has a shorter variance so that the point estimate is neither overestimated nor underestimated. Thus, it's important not only to choose a statistic that does not have a systematic tendency that underestimates or overestimates the true value, but also to choose the statistic whose variance is lower. The sample statistic being an outcome of a chance experiment wherein a sample is drawn out of the population and the statistic is arrived out of that sample. The single value of the sample statistic can be different each time a sample is drawn. The range or interval within which the sample statistic can vary is determined by the width of the distribution, in other words, the sample statistic distribution. A point estimate, that is the sample statistic, despite choosing the statistic whose distribution is centered at the true value and whose variance or standard deviation is reasonably small, does not provide an information on how large can be the error in the point estimate, that is, the absolute difference between the point estimate and the true value. An alternative to the single point estimate is an interval centered at the point estimate with an intention to convey how far can be the true value from the point estimate. What are the bounds on this interval? In other words, what is the width of this interval? What does the width signify, or what does this interval exactly convey? In order to understand further, let's shift the interval from the point estimate to across the true value. In practice, three interval sizes are used. A 90% interval implies a width that captures central 90% of possible values for the sample statistic, in other words the point estimate, when the sampling and subsequently evaluating the point estimate is repeated over a large number of times. Similarly, 95% implies central 95% of possible point estimates, and 99% implies central 99% of possible point estimates. Moving the interval back with the sample statistic or the point estimate at the center implies that the interval constructed with the sample statistic at the center captures the population characteristic, in other words the true value, x% of the times, where x can be 90, 95 or 99%. Just to recap once again, x% of the times mean if the sample statistic is chosen repeatedly, drawing different samples each time over a large number of times, x% of times the interval will capture the true value. This interval is called as the confidence interval, which is not a fixed interval but constructed with the sample statistic at the center, and it moves every time a sample statistic is computed. And the length of the interval represented in percentage is called as the confidence level. Confidence interval is always associated with a confidence level. For example, 95% confidence interval. Commonly used confidence intervals are 90% confidence interval, 95% confidence interval, and 99% confidence interval. Definition: confidence interval Ci for a population characteristic is an interval that includes all plausible values for the characteristic. It is constructed centered at the sample statistics such that with a chosen degree of confidence, the population characteristic, in other words the true value, is captured between the lower and upper ends of the interval. Definition for confidence level. Confidence level is the success rate of the method in capturing the population characteristic in repeated trials over a long run. For example, in 95% confidence interval, the success rate in capturing the population characteristic is 95% of the times in repeated trials over a long run. Thus, the confidence interval with a chosen level of confidence x% provides an interval that captures the population characteristic x% of the times in a long run. How to calculate the upper and lower ends of the confidence interval given a sample statistic? Let's explore now. SS being the sample statistic, the upper end of the confidence interval equals SS plus Ci divided by 2, and the lower end of the confidence interval equals SS minus Ci divided by 2, such that the overall confidence interval is Ci for a given confidence level. In order to make it easy to arrive at Ci, let's move the confidence interval such that it is centered at the population characteristic, that is the true value mu, and ignore the sample statistic SS for the time being. Note that Ci is replaced with I since the interval I cannot be called as confidence interval anymore by definition. The sample statistic distribution is close to a normal distribution if the sample size is large enough. Refer lectures on the following two commonly used sample distributions. 1. Sampling distribution of sample proportion, and 2. Sampling mean distribution and central limiting theorem. Accordingly, in case of sampling distribution of sample proportion, large sample implies n pi is greater than or equal to 10 and n multiplied by 1 minus pi is greater than or equal to 10, where n is the sample size and pi is the population proportion. Similarly, in case of sampling mean distribution, a large sample implies n is greater than or equal to 30. In a sample statistic distribution that is close to normally distributed, 90% interval capture the central 90%, a 95% interval capture the central 95%, and a 99% interval capture the central 99% of the sample statistics in the distribution. Let's consider the most commonly used interval, that is 95% interval, and proceed to estimate the upper and lower ends of this interval. The way to go about is to first estimate the interval ends using the standard normal distribution curve, the z-curve, estimate plus z star and minus z star values, and translate these values back onto the sample statistic distribution. In order to do that, we first estimate plus z star and derive minus z star from plus z star using their symmetry with respect to 0. Plus z star is picked from the z table using the value of the area of the z curve to the left of plus z star. Area of the z curve to the left of plus z star equals area under the z curve within the 95% interval plus the area under the z curve to the left of minus z star. Area under the z curve to the left of plus z star therefore equals 0.95 plus 1 minus 0.95 divided by 2, which equals 0.95 plus 0.025, which in turn equals 0.975. The 1 minus 0.95 in 1 minus 0.95 divided by 2 above equals the sum of the areas under the z curve to the left and right of minus z star and plus z star respectively. Thus the area under the z curve to the left of minus z star equals 1 minus 0.95 divided by 2. Area of the z curve to the left of plus z star equals 0.975 is located here in the z table. Corresponding z value for plus z star equals 1.9 plus 0.06, which equals 1.96. Therefore, plus z star equals plus 1.96, and by virtue of symmetry, minus z star equals minus 1.96. Therefore, upper end of the 95% interval on the z-axis is plus z star equals plus 1.96, and lower end of the 95% intervals is minus z star, which equals minus 1.96. Since the unit for z star is the standard deviation sigma x bar of the sample statistic distribution, transforming the standard normal distribution into the sample statistic distribution with true value, in other words the population characteristic mu, we have this where upper end of the 95% interval equals mu plus 1.96 times sigma x bar, and lower end of the 95% interval equals mu minus 1.96 times sigma x bar. Moving the interval back with sample statistic SS at the center, we reconstruct the confidence interval with upper end of the 95% confidence interval equals SS plus 1.96 times sigma x bar, and lower end of the 95% confidence interval equals SS minus 1.96 times sigma x bar, where, as discussed already, sigma x bar is the standard deviation of the sample statistic distribution. Therefore, the confidence interval with 95% confidence level spans symmetrically across the sample statistic SS and extends between the lower limit SS minus 1.96 times sigma x bar and the upper limit SS plus 1.96 times sigma x bar. The population characteristic, in other words the true value mu, is captured by the confidence interval generated by the above discussed method 95% of the times. The general expression for the confidence interval is SS plus or minus z star times sigma x bar, where z star is the z critical value that depends on the confidence level. equals 1.65 for 90% confidence level, 1.96 for 95% confidence level, and 2.58 for 99% confidence level. The value of sigma x bar depends on the kind of the sample statistic. We discussed two kinds of sample statistic distributions, namely 1. Sampling distribution of sample proportion, and 2. Sampling mean distribution. We will understand how to arrive at the value for sigma x bar for each of the two distributions in the next lecture. Point estimate and confidence interval part 2. That brings us to the end of the lecture on point estimate and confidence interval part 1. See you back with the lecture on part 2. Thank you and bye.